All right, so the last speaker for today is Anna Abasheva from Colombia, and she will talk about Shafarevich-Tate Twists of holomorphic Lagrangian fibrations. Please go ahead.
Hello, everyone. First of all, I'd like to thank you for inviting me. It's really a pleasure to give a talk in front of you. So my talk is going to be about Shafarevich-Tate groups of Lagrangian fibrations, and it's based on two papers. One joined with Vasily Rogov, has the same name as my talk, and another also has the same name as my talk, but it's the second part of the paper. So I'll start with a few definitions. I expect that most of you, if not all, know the definition of an irreducible holomorphic symplectic manifold, but I'll have to define it again because in my talk I'm going to make a distinction between irreducible holomorphic symplectic manifolds and hyperkähler manifolds. That's because I work in the category of complex manifolds, which may or may not be non-Kähler, and we'll encounter non-Kähler manifolds in this talk. So for me, an irreducible holomorphic symplectic manifold is a compact, simply connected complex manifold with a complex holomorphic symplectic form sigma, such that the space of holomorphic two forms on X is generated by this form. And I call X hyperkähler if it's irreducible holomorphic symplectic and Kähler. And there are examples of irreducible holomorphic symplectic manifolds which are not Kähler. So irreducible holomorphic symplectic manifolds often admit morphisms that are called Lagrangian fibrations. Lagrangian fibrations are by definition morphisms with connected fibers onto a normal variety B, such that the restriction of the holomorphic symplectic form on smooth fibers is zero. And in all known examples of Lagrangian fibrations, the base is isomorphic to Bn. It's conjecture that it's always Bn. We know that it's the case if B is smooth, but in general, it's still a conjecture. In my first paper on the topic, I used the assumption that the base is smooth, but luckily I managed to get rid of this assumption in my second paper, and that's because the base behaves in many ways as Bn. For example, if you look at the cohomology groups of the sheaf of reflexive differentials on the base of a Lagrangian fibration, then it turns out that the cohomology groups are the same as for Bn. And this result can be used for some computations in the paper. So let me now introduce the main character of my talk. This is the Shafarevich-Tate group. I define it for a Lagrangian fibration, but it can be defined in a more general context, and I'll comment a little bit on it later. So for Lagrangian fibration, I define it as the first cohomology group of the sheaf O to naught of X over B. It's a subsheaf of the sheaf of automorphisms, of relative automorphisms of X over B, and you can think of it as a connected component of unit of this sheaf. I'll define it more precisely later. But for now, I'd like to explain that Shafarevich-Tate group, this definition looks a little bit abstract, but actually it has a very clear geometric meaning. We can represent every class in the Shafarevich-Tate group by a check class cycle. So what we do, we cover the base B by open subsets, and then we have automorphisms over intersections of these open subsets. And these automorphisms satisfy the cycle condition. Then we can glue a new variety X using these automorphisms. So over each open subset, it looks absolutely the same as the initial Lagrangian fibration, but then we just reglue it differently. And we get a new variety which also admits a fibration. It has the same fibers. I call it a Shafarevich-Tate twist of X. And as I said, this definition works in a more general context, and in particular, Kolar, in his recent preprint, defined Shafarevich-Tate group for a billion fiber spaces. And his definition is the same module as the definition of a knot of X over B. It is expected that our definitions are the same, but for now, I don't know the answer. So let me just tell you what definition of odd knot X over B I use. First, I define the sheaf of vertical vector fields. It is heuristically it's just the sheaf of vector fields which are tangent to fibers, but formally it's the kernel of the map from the tangent shift of X to the pullback of the tangent shift of B modulo torsion. And I say that an automorphism is in odd knot of X over B if locally it can represent it as a flow of a vertical vector field. And it's unclear to me whether it's the same definition as in polar. Polar defines odd knot of X over B as a set of automorphisms that restrict on each fiber to an automorphism which lies in the connected component of unity, which follows from this definition, but also Color uses something related to neuron models, and it's unclear how to translate the language of neuron models into the language of vertical vector fields. But okay, let's see what can we say about vertical vector fields. It turns out that this sheaf is isomorphic to many other sheaves. First of all, we have holomorphic symplectic form. It induces an isomorphism between omega x to tx. And using this isomorphism, we can construct an isomorphism from the sheaf of reflexive differentials on B with the push forward of the sheaf of vertical vector fields. And also it turns out that this sheaf, the sheaf of reflexive differentials is isomorphic to push forwards, higher push forwards of X. That's the result of O. And this result can be used to compute the homology of the sheaf of reflexive differentials, the result that I mentioned before. In my paper, I was concerned with the question of when Shafarevich-Tate twists are scalar and when they're projective and when they are non-scalar, because my definition is purely differential geometric. So the result can easily be a non-scalar holomorphic symplectic manifold. But before I state my results about the properties of Shafarevich-Tate twists, let me tell you something about the structure of the Shafarevich-Tate. It admits the structure of a topological group. So I denote the connected component of unity of SHA by SHA naught. And it turns out that SHA naught is a quotient of H02 of X by the lattice by finally generated subgroup H2 of XZ. H02 of a holomorphic symplectic manifold is one-dimensional, so it's kind of a curve. But the problem is that this group doesn't have to be a lattice. So SHA naught may be non-Hausdorff, and in general it is non-Hausdorff. And also we can describe to some extent the discrete part of the Shafarevich-Tate group. It turns out that if we tensor it by Q, then it becomes isomorphic to H2 of the first push forward of Q. Well, this is one of the groups that appears in the array spectral sequence for Q, and we know that there is a differential D2 from H0 of R2 pi star Q to H2 of R1 pi star Q. And it will turn out that Shafarevich-Tate twists with respect to an element which lies in this image behave very differently from those with respect to an element which doesn't lie in the image of D2. And before I state the main theorem, I'll introduce a little bit of notation. For an element phi in a Shafarevich-Tate group, I denote by phi bar its image in H2 of R1 pi star Q, where we identify H2 of R1 pi star Q as the quotient of SHA by SHA naught, well, tensor Q. Okay, great. When is a Shafarevich-Tate twist scalar? It turns out that if we restrict our attention only to classes whose power lies in the connected component of unity, then all such twists are scalar. And also we can describe explicitly which of these twists are projective. So assuming that X is projective, then X phi is projective if and only if phi is torsion. And it's pretty easy to describe torsion elements in the Shafarevich group because of this description. As I said, SHA naught is a quotient of C by some finally generated group. So, well, torsion is dense in this group. And also we can describe the case when a sheaf is not Kähler. Namely, if we look at a twist by an element whose element phi, such that phi bar is not in the image of D2, then X is not only non-Kähler, but it's also not in Fujiki class C, which means that it's not bimeromorphic to a Kähler manifold. And there is an example of this. We can consider, so first let's consider an abelian surface, which is a product of elliptic curves. Then we can take the Hilbert scheme of points of the abelian surface A and one of the elliptic curves E. And eventually, after massaging it a little bit, we'll get a fibration on the Kummer, generalized Kummer variety of A, Kn of A. I'm not going to describe how to do that. That'll take quite a lot of time. But you probably already know that. We can also perform a similar construction with a cadaver surface. What is a cadaver surface? It's a Shafarevich-Tate twist of A, and it's non-Kähler. It's non-Kähler, it's not from Fujiki class C. And we can use a similar construction to obtain a so-called Bogomolov-Guan manifold, which also admits a fibration or a PN. And it turns out that in the same fashion as was a Shafarevich-Tate twist of A, the Bogomolov-Guan manifold is also a Shafarevich-Tate twist of the generalized Kummer variety. And it's non-Kähler, as follows from this theorem. Well, it was known before this theorem, but it also follows from it. And also, some general results about Shafarevich-Tate twists can be used to compute some homology groups of Bogomolov-Guan manifolds. Namely, it turns out that we can describe a lot of homology groups of twists. First of all, from the definition that I gave, it's not 100% clear that they are irreducible holomorphic symplectic. But actually, they almost are. First, there is a holomorphic symplectic form on a Shafarevich-Tate twist, which is quite easy to construct. What is harder to prove is that the vector space of holomorphic two forms is generated by a holomorphic form. And also, I didn't manage to prove that twists are simply connected, but they have a true first Bethe number. The second Bethe number is more interesting. It turns out that there are exactly two cases depending on whether phi lies in the Shafarevich-Tate, the element with respect to which we take a Shafarevich-Tate twist lies in the image of D2 or not. In the first case, the second number will be the same as the second Bethe number of X. And also in this case, there's a class in the second homology of X phi whose restriction on all smooth fibers is ample. Not just Kähler, but ample. And also, okay, what's the second case? The second case is when phi doesn't lie in the image of V2. And in this case, things become kind of weird. The second Bethe number is equal to the second Bethe number of X minus 1. And in this case, all classes in the second homology group of X have trivial restriction on fibers. So obviously that can't happen with Kähler manifolds. And also they can happen with Fujiki class C manifolds. So this is exactly the case when X is not Fujiki class C. For example, a Bogomolov-Guan manifold. I'm not going to prove this result, but I can give you some intuition why it's true. We have one very specific class inside the second homology group of X, which is the pullback of an ample class on the base. And it turns out that if X is hyperkähler, then the orthogonal to eta is equal to the kernel of the restriction map from H2 of X to the fiber. What I mean by an orthogonal, I mean orthogonal with respect to the Bogomolov-Fujiki form, which is a non-degenerate quadratic form on the second homology of any irreducible hyperkähler manifold. We can write the second homology of X as a direct sum of eta orthogonal plus some Kähler class of C, which restricts non-trivially to every fiber. And in the first case, the second cohomology of a twist looks the same. So it never changes. It just remains the same for every twist. But what can change is whether we have an additional sum on C or we don't. So in the first case, there's still a class which restricts non-trivially to every fiber. In the second case, the second cohomology group consists just of 8 pair. And what's interesting, it still admits a Bogomolov Fujiki form, but in this case, it is degenerate. But unfortunately, my description, this theorem wasn't complete because it says nothing about what happens with classes which lie in the image of D2, but which are not torsion, which are not torsion in the discrete part of the Shafarevich-Tate group. First of all, I don't know if these classes exist. I don't know any examples when D2 is non-zero, but there might be some examples. So it would be interesting to understand, to construct any examples if they exist, of course. And conjecturally, assuming that this case occurs for every phi which is in the image of D2, X phi would be still a Fujiki class C, which makes sense because there's a class which restricts to an empty class on every fiber. But it would probably be non-Kähler. Well, unless we are in the first case when some power of the class is in the Shannon. And examples of holomorphic symplectic manifolds which are in Fujiki class C but which are not Kähler, they exist. So it's possible. And finally, in the remaining few minutes, I'll just give you an overview of the proof. The proof is very long, so obviously I'm not going to be able to explain everything, but I'll just explain you the main steps. The proof starts with the statement about projectivity. So assuming that X is torsion, we want to prove that phi is torsion if only if X phi is projective. And we use a patching argument here. So as before, we cover B by open subsets, and the preimage of this open subsets Xi is, of course, ample over, projective over UI. There is relatively ample line bundle. And we need to patch these line bundles into a relatively ample line bundle on X phi. If we can do it, we are done. And it just said that if phi is torsion, then we can construct a gluing function between these line bundles and also massage this gluing function a little bit so that it satisfies the classical condition. Great. After we're done with the first step, we are almost done with the second statement about Kählerness, because Kählerness is an open property, and as I mentioned before, torsion elements are dense in Shannon, and that means that Shafarevich-Tate twists are Kähler for all elements of Shannon, except maybe for elements in an over-dense subset. After that, well, we want to know that all twists are Kähler, not just all except for an over-dense subset. And that requires a quite complicated limit argument, which uses a lot of machinery. So basically, we want to prove that the limit of hyperkähler Shafarevich-Tate twist is also hyperkähler. It uses global Torelli theorem. It uses Pericles results on limits of hyperkähler manifolds, and also uses some results of Greb-Land-Rolansky about existence of Lagrangian fibrations on non-Kähler, non-projective hyperkähler manifolds. So it's quite complicated, but it does a job. And I'm almost out of time. So thank you so much for my attention. This is all I have to say. I will be happy to answer questions.
Thank you so much. Any questions? Comments? Okay, if not, thank you again.